Cool. Yeah.
Thank you for joining us today. I am Ruth. I'm the CIBS-EN London Vice Chair, and I'll be the moderator today. Welcome to our new webinar on climate responsive design. This presentation will be recorded, so you can turn off your camera if you don't want to be. Please put your microphones on mute. If you have any questions, please post it in the chat section. We will have time after the presentation for a QA session. For this CPD, we have two speakers from Chapman BDSP. Our first speaker will be Deepika Singhal, who is an associate environmental consultant with more than 12 years experience within the sustainability sector. She's involved in industry initiatives like LETI, Future of London, and others to lead from the front. Deepika was also a nominee for the Women in Construction Awards and is on the committee of National Association of Women in Construction, London and Southeast England. Aman Kahira, our next speaker, has more than 10 years of industry experience as an environmental consultant and now leads Chapman BDSP's internal research and development arm, Labs. With a background as an architect working in Malta and Spain, Aman has experience in a variety of environmental tools for indoor and outdoor thermal comfort, daylighting studies, and computerized fluid dynamics. He has particular interest in the early integration of environmental principles during the design process. Aman has lectures at the Architectural Association's School of Architecture in London and has participated in smart geometry conferences, workshops in London, Munich, and San Francisco. Thank you both for being with us today. I'll now leave the platform to Deepika.
Thanks, Ruth. Thanks for the introduction. I'm going to share my screen now and hopefully it will all work. Right, can you see the screen? Do you see the presentation now? Okay. So hi, everyone. Thanks for taking out time this afternoon. So as Ruth said, the topic is climate responsive design, but it is extremely important factor in achieving zero carbon building. So I have twisted the title slightly to call it Importance of Climate Responsive Design in Road to Zero Carbon. Ruth has given both of our introductions. So I'm an associate environmental consultant at Chapman's, and Harman is head of labs. It's not a chemical lab, it's an environmental design lab. Let me just clarify that. What it means is that we look into everything new or anything interesting that we want to research in. Harman, with his very technical and analytical brain, looks into everything in detail, right from GLA energy assessment guidance to battery storage to overheating to landscape design, you name it, and we do it. We also use it as a collaboration tool with our peers and any architects we're working with who would like to research into a particular topic. So that's a great initiative by Chapman's for keeping some resources and time aside for these things. The ethos of all our projects is this relationship that we call a planet to person to planet relationship. So starting from looking at the site climate, then master planning stage, looking at how the buildings should be designed in a particular microclimate or climate, then looking at buildings design, occupant behavior and how they perceive the building, and then giving back to the planet in terms of reducing embodied carbon and going for the certification scheme. So it's a relationship that we follow in all our projects. We always suggest our clients to act early in the project because with these passive design measures are easier to investigate and implement at early stages of the project rather than leaving it till later. Also, we all know we are in this climate emergency, so it's really important to act early in the project. Like our peers, we have signed the construction label. That doesn't mean our job is done. We are striving to carbon in all our projects, and also how we operate our business. Obviously, we have this big target of having all new buildings zero carbon by 2030, and all the existing and new buildings zero carbon by 2050. So that's a massive challenge ahead of us. In terms of talking about the road to zero carbon, I would like to say it's an 8-step approach. The first two things that we are going to talk about, the first one is obviously passive design optimization and reducing demand and consumption of the buildings. These are the two topics that we'll be covering today. There is obviously all of them are so involved that there can be a CPD on each of those steps. But the first two steps are the ones that we are going to cover today. So now I'm going to hand over to Herman, who's going to talk about this project in Nairobi. Herman, do you want to share your screen?
Yeah, thank you. So, yep, perfect. Thanks, Deepika. So the first project is a project in Nairobi, as Deepika mentioned, and the first thing which we do on a project is to first look at the climate, which then suggests to us what passive design strategies would be most adequate for that location. So in a way, quite naturally, one would say, it's near, just below the equator in Africa. Definitely, we'll have to use cooling. It's a very hot place, etc. But in looking further into the actual climate data, we realized that due to the altitude of the site, the temperature was relatively rather mild compared to other areas along the equator. And we saw that there's potentially a good opportunity to use natural ventilation as a passive design strategy on this project. So that was in a way like looking initially at the temperature on the first graph. Then looking further, of course, it's a sunny place, but we try to differentiate between diffused and direct solar radiation. So the direct solar radiation is the amount of radiation coming directly from the sun. You can draw a line, a straight line. However, the diffuse component is coming through this sky dome, where you have radiation coming to a scattered manner. And the difference between the two is that with the direct solar radiation, we can protect from it through geometrical solutions, like an overhang, for example, for a south facade, typically for our latitude in the UK. However, the problem with the diffuse solar radiation is that it's not geometrical. It's coming through this scattered sky dome. And due to that, it will be difficult to use a louver or a fin to try to shelter from that radiation. And so typically one would look more at enhanced G values, for example. So that was a very also good insight that we got, which is shown in the second graph, which is also related to the third graph, which shows you the cloud coverage. Typically, when you have a large amount of cloud coverage, you have a higher amount of diffuse solar radiation. So that was a very good initial insight on the site, on the location. Then looking further into how we can achieve comfort for this office. So we looked at the period which falls within the comfort band and the amount of time which is below the comfort band, but which we can still retain in comfort using the internal heat gains that are produced in the space through the occupants, equipment, lighting, and of course, most significantly, solar radiation. And on the other hand, on the other side of the comfort band, we have the percentage of time for which we can still retain the space within comfort through the use of natural ventilation as a passive cooling solution. And that showed us that using passive design, we can pretty much have the building operating within comfort purely by using internal heat gains during winter and ventilating further during the summer period. And when we looked at other, let's say, case studies or examples of what's happening around the site, so most of the other towers were in a way like climate rejecting. So they try to produce a building envelope which segregates the outdoors from the indoors, and the indoors is conditioned through air conditioning. And we didn't want to go with that option. We saw that there's strong potential for a passive design solution. So we saw that they had like very few openable windows, the cores sometimes located on the facades, irrespective of what's happening to the daylighting, etc. And most of them, these spaces were rather gloomy, both because they were using tinted glass and also because of the location of the cores. So we learned in a way from these examples to know what we should avoid in a way. And summarizing the lessons learned, we wanted to use solar shading to reduce the internal heat gains during the summer period. We wanted to have good daylighting rather than relying on artificial lighting. And we still wanted to retain good external views for the place to be pleasant. And we wanted to use the natural ventilation as a means to retain the space within comfort during the summer period, or the warmer period. So when we're looking at the different orientations, we saw that the east and west were the orientations which received the highest amount of solar radiation, mainly because of the altitude and the altitude of the sun when the sun passes across the east and west facades. So it gave us some initial indications, and then the inclination of the tower made small difference, but not as significant as the orientation. We also looked into we did CFD to show what is the wind pressure, which can give us an indication of what wind speed we're getting for our natural ventilation. And then we were setting thresholds or design targets with regards to daylighting. So we were targeting the 2% daylight factor, which would account for which would translate in this climate to 200 lux on an overcast sky condition. That is when it's rather cloudy, so cloudy that you cannot spot where the sun is, which is not as common in this location. So we know this would be a worst case scenario, while with typically one would be easily over 250 lux, over 200 lux. And we also had a similar threshold for the number of hours, which we would allow exceedance beyond the comfort band. So rather than having a fixed comfort band, we were using the EN 15251 comfort band, which takes into account that people's expectation of the indoor temperatures relate to the previous experience of a person over the previous 7 days. And so then we're looking at, let's say we had different palettes or different tools which we were looking into to try to get this cohesive passive design strategy. So one of the aspects which we definitely look at is the glazing ratio, then looking at what percentage of the window will be openable or not, and then the type of shading that we would use, and then the type of glass that we would use. So starting initially with the shading devices, we're testing different ceramic baguettes of different spacing and different forms, and trying to identify the benefits of each of them. So one of them was definitely the view, especially the view looking downwards towards street level, and then we're looking at how effective is the ceramic baguette at generating shading. And also in terms of the impact of the baguette with regards to obstruction to the airflow. And while, let's say, in a latitude like London, the third baguette might work rather well, especially for a south facade. In this location, due to the large amount of diffuse solar radiation, the first two baguettes were performing in a way better because they were helping to protect a larger part of the sky dome, from a larger part of the sky dome. Then we're looking also So daylight, with regards to daylighting, nowadays we look more to what we call climate-based daylight simulation rather than daylight factor. So the daylight factor, as you can see, will show a performance irrespective of orientation. While when you look at the actual amount of lux, the amount of light falling on the grid, we can see now the impact between what happens at 9 o'clock, at noon, and in the afternoon. So we will look also at that. And then trying to decide on the openable percentage of the windows, but not purely on opening the window, but also the location of the openable window. And the most effective solution was to have two openings. When one would have two openings, one would have a less turbulent flow through the space, because generally the lower opening would tend to bring in the cooler air from outdoors, and then warmer air would be seeping out through buoyancy to the high level window. Then once again, we're looking at what is the impact of changing the percentage of facade openable area with regards to the overheating criteria. And then we were adding the different passive design strategies. So first we started with let's say rules of thumb, percentage of openable area for the window. Then we enhanced the selected glass. Then we're doing daylight linking. That is, the artificial lighting would switch off when there's enough daylighting in the perimeter zone. Then we're using the ceramic baguettes and seeing the impacts of those. And then finally, we did some combined optimization, fine tuning on the selection of the glazing, the baguettes, and openable area. And it got us to a point where we would be beyond the comfort band only for 3.8% of the time, which is a very successful percentage considering the location. This is the project, and yeah, which actually we won an award very recently for the MVP of the tower.
Right. Share my screen again. After all these clever passive design measures, I'm going to touch a bit on reducing the demand and consumption further. So just an example, this is closer to home. This is in Gloucester, one of the examples that we've been working on. It's an office building, and just very simply, the concept of mixed mode and how this can help is what I'm going to show in these slides, and then go on to a project example. So this is what the floor plan looked like. I hope you can all see my screen. This is what the floor plate initially looked like. So to increase the potential for natural ventilation, we applied a basic logic of reducing the floor plate depth, and then having a thumb rule of 6 meter peripheral zone, 3 meter circulation zone, and 6 meter peripheral zone. So in total 15 meter depth, floor depth, to have an effective cross ventilation on all these floor plates. In terms of control, which is always challenging in mixed mode, we proposed a traffic light system, which will sort of nudge the occupants to open their windows when the temperature exceeds a certain level. So just to give you a bit of understanding of the project, so the 3 zones look like here, zone 1, 2, and 3. The window, each window module was something like this on the screen. So the 2 split windows on the sides were openable. They might not look like a lot, but in total, that's about 30% of the total floor area. So still significant opening area. Looking at different scenarios, a scenario with only natural ventilation, a combination of natural and mechanical ventilation, and only cooling, we tested the cooling demand and what impact this would have. So just to explain the graphs on the right-hand side, yellow is the case with cooling only, so that's our base case. Green is the case with mixed mode ventilation, so we're assuming that the windows will open at 21 degrees and close at 23 degrees as the cooling thermostat is set to 24 degrees, and then an intermediate case. And the reason for testing the intermediate case is because we are relying on occupants to open those windows. Some might decide to ignore the traffic light, or they might be busy. You might have 50% occupancy in the offices, so there could be different scenarios. So we decided to test an intermediate case where only 50% of the windows will be opened. So looking at the results, just with mixed mode ventilation, what we found out was that during the peak summer months, that's between May and September, the cooling hours or the cooling operating hours can be reduced to 72%. That's a significant number. Even if the windows are only 50% of the windows are open, that could reduce to 48% of the time. So again, another significant number. Also, if we look at the monthly cooling demand, then during the peak hours, which is within this red dotted line, you'll see that the cooling demand is reduced significantly, and anything outside that peak months would be dependent mostly on natural ventilation, as the cooling demand wouldn't be as high. So that's a big I would say green flag for incorporated mixed mode. Obviously, it's challenging, but still really useful. So now I'm going to show an example, a project example where all these principles were applied. That's LSC, CBR building. So the concepts that were applied, the environmental concepts applied to this project included outdoor comfort, flexibility and adaptability, natural ventilation, daylight, solar control, and all the rest. So the brief was obviously quite challenging, and then it gave us a lot of opportunity to work on it. So starting with the space users, we started having these early discussions with the LSE staff and users, and started looking at what spaces. I'm not sure if it's legible, but I'll just read it out. So these are the type of zones or spaces like the cellular offices, meeting rooms, open plan, academic spaces, auditorium, and others. And over here, we have the environmental factors like daylight, natural ventilation, solar access, view out, and others. And the whole idea of the study was to understand what environmental aspects will be desirable, not desirable, critical or not critical in these different zones. So for example, if you're talking about a breakout space, daylight and natural ventilation is desirable, solar access not as much desirable, view as definitely desirable, and so on and so forth. So for each zone, the study was done because it's then easier to locate it on the floor plate. Again, looking at the occupancy schedule, we looked at different spaces and at what time of the day, week, and year they'll be used. So for example, single office or cellular office will be mostly used between, say, 7 in the morning till 8, 9 in the evening, and then obviously used throughout the year. While if you're looking at a breakout space, it would be used at intervals during the day, but mostly throughout the years. The whole point was to understand the requirements and getting that understanding early in the project. Similarly, because the idea was to do a detailed energy analysis, we looked at what small equipment these spaces will have and how many numbers of those equipments these spaces will have. All this helped into a zoning strategy. So looking at the public and private zoning, we decided with the architects that the ground and the basement floors will be more for public, areas. The floors above, say first, second would be more semi-public, so say collaborative spaces, and the floors above would be semi-private or private, so with cellular offices, for example. Going by the same logic, the lower floors in terms of occupancy will be high occupancy, so the auditoriums, big lecture theaters, they will be in the basement and ground floor. And then the medium to high occupancy spaces on floors above, so that's your collaborative spaces again. And then floors above would be low and medium occupancy. What this finally led to was a mechanical strategy where the lower floors with high occupancy and public areas were decided to be were decided to have active cooling. So these are the spaces like auditorium and lecture halls. The spaces above would have mixed mode because these are bigger spaces, more collaborative spaces, and the upper floors, which are smaller cellular office, they'll be all naturally ventilated. So it obviously the project was quite challenging, and trying to balance all those factors meant output from one software will be input in another to finally get to a result. And obviously it involves some really clever algorithms and complex modeling. I started looking at the irradiation mapping and what the solar exposure will be on the facade, and then undertaking a thermal modeling to see what the maximum fin depth should be to avoid excessive solar gains on the floors and avoid overheating. Applying that logic, we came up with a facade optimized design. Obviously, I'll show you something after this slide, but this facade optimization made sure that the floors do not get excessive solar gains and they stay within the comfort range that is required to avoid overheating. So hopefully this video will work. Right, it is a bit slow. I'm not sure if you guys can see it, but basically it looks at, it tests the fin depth at each bay to figure out the optimized depth that is required to get the solar access levels that are desirable to avoid overheating. And then that solution in total, sorry, the video is really slow. So, okay, let's try if this works. Not really. Harman, can you see it working? Okay, no. This is not great. It's just extremely slow. So I'll explain it in the what this video is doing, but basically it's showing all the parametric modeling. Okay, this is working now. So it's showing all the parametric modeling and how those two factors, solar access and overheating, were controlled through this design of solar fins. Also then, to decide the spacing between those fins, a daylight study was done to sort of balance daylight factors achieved on the floor plate to the overheating ratio. This is the final sketch of what the facade looked like and a mock-up. The building is now complete and it's open for visitors to go and have a look around. Also something about flexibility, which was really interesting because obviously there are so many different types of spaces in this building. We looked at different flexibility and different modules and what fenestrations we have for facilitating natural ventilation, for example. So a combination of high-level automated windows, manual windows, fixed windows, internal doors, glazed partitions, and others. We looked at what typologies we can have on each floor. So there are some floors with cellular offices on each side and circulation space in between. Some floors have cellular offices on one side and open plan collaborative spaces on the other side. Some will have cellular offices and double height spaces on the other side. So it was a combination of natural and mechanical ventilation, especially on lower floors where we were going with a mixed mode ventilation option. On the floors above, where we have completely naturally ventilated floors, we did a detailed overheating study to look at if we meet the TM52 criteria. So the greens, obviously, as expected, the spaces next to the windows, the peripheral spaces, they met the overheating criteria. The spaces which were more internal, they marginally met the requirements, but none of them actually failed. So that was a big positive. Applying all these different factors of solar access and open spaces and cellular offices, we provided architects almost a palette to decide where the spaces are going on which orientation. So for example, if you look at this diagram here with different zoning, if you look at zone 2, that's the easiest one probably, where you don't get as much solar exposure. There's no potential for natural ventilation because it's an internal space, so it's good for circulation. But if, say, for example, we pick up zone 5, Zone 5 gets decent solar access because it's close to the windows. It has good potential for natural ventilation, so it could be used either for big open areas for students or admin staff or breakout space. It could be used for circulation as well, but that would be a waste of space. But basically, we started giving these zoning diagrams to the architects to decide their floor space or floor layout. So in summary, the building achieved outstanding in construction. It has all these strategies that I've already talked about, but in terms of clean technology, it has biofuel CHP. For those who don't know much about biofuel CHP, it's a combined heat and power plant which runs on the waste from pharma industry, and there's one provider for this waste fuel who basically takes a boat all around, collects all the waste from the pharma industries and delivers it to the site. So the only carbon footprint is actually in transportation. It also has PVs to offset the demand. Almost 70% of the accommodation is naturally ventilated. And we're not doing a CPD on embodied, but I thought it would be good to just touch on that with the measures with recycled aluminium and other measures, we could reduce embodied carbon to 30% of the total. Arman, on to you.
Thank you, Deepika. So trying to explain a bit the process that we take in terms of trying to optimize the design. So this is a sports hall. So we have a target of 800 lux or above for the court and 300 lux or above for the audience area. So that we start first with the thresholds or the design targets, and then we put in the design variables. That's what we put into our, let's say, our scripts. For example, in this case, we know, of course, it depends on the design solution. In this case, let's say we're going for north-facing openings. So we're just gonna vary the angle. And we know that given that more light is required in the center, we would have some element of gradation of how this opening varies between the center and the edges. So we have those two variables, the angle of opening and this gradation. So those are our variable parameters, and in yellow, we have two variable parameters. Then we have the actual analysis. So in this case, we would be simulating how much light is falling in the space. And then once we get results for both the audience area and the court area, we compare, are we meeting the threshold, yes or no? If we meet it in both of them, then the design is a good solution. And we would run for a range of values. And we would get different results, basically. And once we have run a number of them, then we can identify which item or which solution. Often you have more than one solution. Which solution would have met the criteria. And in this case, this solution would be an adequate one, for example. So this is, in a way, like the approach that we take. Going to an actual application of this on a project, once again, is for the London School of Economics, but this time with Grafton Architects. This one is still in construction. Just some images from competition stage when we won during the competition. It should be a very beautiful sculptural building. And as Deepika mentioned earlier, when she was showing the plans and how they were cut to allow for ventilation, in a similar approach here, we introduced these design team. We're introducing these different cuts within the volume, both to allow a good amount of daylighting and also to allow a narrower floor plate so we can have cross ventilation. And you can see a very good performance with regards to daylighting. While if you look at the actual site footprint, one could have easily ended up with a very deep plan design. We have even good amount of daylight even at the ground floor level. And so we're looking both at daylighting, at the same time we're looking at the thermal comfort. So we would typically do the solar radiation mapping studies on the facade. And using this information, once again, we were able to simulate that and come back with different recommended glazing ratios for the different orientations. So what we did here is, so while this was the solar radiation mapping, now what we're showing in this image here is the coloring is a legend. So what you see on the facade is the recommended amount of glazing ratio for that particular area. And in addition to that, while we have a higher amount of glazing area in sheltered, protected areas on the lower floors, the higher amount of opaque element on the higher floors also help to reflect light back down to the floors below. So that was also a helpful part of the strategy to get good daylighting on the lower floors. Which once again, once this will be built, it should be a very sculptural design. And in addition to that, then what we did is, because normally we wouldn't want to tell the architect, so this is the solution. We would like to support the architect, giving the architect a selection of solutions. So what we did here, we have different glazing ratios shown horizontally and vertically. The rows show the different percentage of openable area of the facade. And using that information, so whenever it becomes green, then we're telling the architect that, okay, go ahead, it's a good design. And we're doing something similar with the daylighting in the lighter green below. And then we would do that for all the different parts of the building. So we would have different recommendations of different glazing ratios and openable areas. And that was so similar work with Grafton Architects, but using similar principles. This is the Toulouse School of Economics, which was also recently finished. And this is a much earlier design, also in collaboration with Grafton Architects, the Bocconi University in Milan, where there were also this similar design of having these light shafts, which are actually sculpting and forming the design. So in a way, many times there is this concept that sustainable design or environmental design can become boring, just a PV at the top. While in reality, once we have a truly climate responsive solution, it can be quite an exciting also outcome. This is a master plan which we're working on in location in the Mediterranean, and so this is to show then the approach at a macro scale. So typically the interventions which are carried out at an earlier stage in the design, in the design of the master plan, can have quite an impact on what potential passive design strategies we can apply. So for example, if we have a space which is surrounded by tall buildings and there is no access, no proper access for natural ventilation, then we cannot really apply natural ventilation so easily anymore. So it's important to have this approach that Deepika mentioned earlier, this people, planet, people kind of approach that we look at the macro scale and then back to the building scale and so on. And what we try to do here is to have a tool to help us provide the massing. So what we did is we did a CFD study where we had a CFD study for different orientations, for 16 different orientations, to see what would be the wind pressure on each of these orientations. And we did this for 3 types of proximity with neighbors. So we had one scenario where the wind is coming and the distance between the adjacent building and our building is quite far. Then we had a medium scenario, the scenario when the neighboring building would be close to us. So we ended up with these different figures for the different orientations. And then what we are doing is, for every hour of the year in the climate and the weather file, we would look at where is the wind coming from at this hour. It's coming from this side. Okay, so the angle of attack is this one. We would choose that particular phase of the simulations. Then we see at which floor we're studying at the moment. So we look at that particular window. So then we would pick up the pressure coefficient, which we had from those CFD figures that we had before, yeah. And using that, we can get back the actual wind speed that would be passing through a given window on that facade. And we did this for automatically in an automatic way for all the hours of the year for any given geometry that we put in. This allowed us to have a combination of simulations here. So we're looking at solar radiation, in this case, we want to reduce solar radiation in the summer period. We had what is this percentage of sea view that we have, which was quite important for a site by the sea. What is the amount of vertical sky component, which is an easy way how we can get an understanding of the daylighting availability. And we had this average wind speed, which was being measured through this computation. And we were plotting all these different solutions. So we have 3 axes, the average wind speed, view and daylighting on this axis, and solar radiation here. So then what we would do is, we say in this case, we would want a solution which has low amount of solar radiation, high amount of wind speed, and good view and good daylighting. So this would be, let's say, an ideal design solution would be one of these ones. And this, in a way, was how we helped to recommend some masking solutions. Once again, there isn't one good solution. So all of these 1, 2, 3, they would all be good solutions or better, which is performing here, for example. That's it. So it was basically summarizing. We look first at the climate whenever we get to a project, and then we look at the surroundings. How is the surrounding also generating these different microclimates for our design? Then we look at building scale, and then how that building is affecting the occupants, and finally how is the building affecting back both the environment and the neighborhood.
We still have a couple of minutes before the
okay. Go ahead.
No, go ahead. Because I was about to say we still have a couple of minutes before the end of the conversation of the presentation, and feel free to drop any question that you wanted in the chat section. Have you finished, Erman?
Yeah, we're done. Yeah.
Congrats, you are just in time. So we still have like 15 minutes for to answer any question. So we have one from Jessica Cassian. Great presentation, Dee and Herman. I would like to ask, since there are a lot of data available on occupancy comfort for non-domestic, what lesson learned could be applied to domestic project to improve indoor thermal comfort?
Yeah, that's an interesting one. Harman, do you want to go first?
So for domestic or non-domestic?
Domestic. The question is for domestic, how it could be applied to domestic.
Yes. So in a similar way, so the measures that or the methodology that we used in the simulation shown would be relying on EN 15251 comfort band, which is basically using the CIPSE TM52 methodology, which is. It is very similar to the methodology applied for domestics uses, which was published more recently, TM59. It basically takes one of the criterions of TM52. And so the lessons learned are typically very similar. There's one additional criteria, though, for the residential, which is, so there is research which shows that trying to sleep at a temperature which is beyond 26 degrees can be a bit uncomfortable for some people. When we say temperature, by the way, we always refer to resultant temperature, which is an average, typically the average of air temperature and the surface temperatures of the room. So we always measure that temperature. And so there is one issue, which is if you have very high thermal mass, there could be the potential of warmth storage within the building that eventually can start releasing during the night, which can cause discomfort during sleep. But otherwise, all the lessons learned with regards to the use of openable windows and having the right amount of openable window and the right amount of solar shading is definitely the first 2 major steps. And many times even the actual massing can help. Massing and its orientation can help to already solve some problems before we look at facade level. But in addition to that, when it comes to domestic, it's typically, I would say, is that aspect with regards to the evening, not to have this too much warmth stored in the building.
Yeah, just to add to that point, I would say, Armin, obviously it depends on what context, what site context we're talking about. But obviously we've talked about a lot on mixed mode and cool to reduce cooling because they were all commercial projects, non-domestic projects. But when we're looking at domestic projects, heating becomes a bigger issue. So passive design and passive house plays a big role in that, in reducing the heating demand. So there is a lot which, maybe another CPD on domestic buildings. But yeah, there's a lot of lessons can be learned from the same analysis that's done on these projects.
Thank you both. We have another question. What software was primarily used for your analysis?
So for thermal comfort, we rely a lot on TAS DSL. Actually, Deepika had showed one slide. It showed the selection of
which show all the softwares, all the tools.
So we rely a lot on.
Then we'll see it, but there's a combination of lots of softwares, but a lot of parametric modeling tools, Ladybug, Rhino, Grasshopper, and then the thermal modeling tasks.
Yeah, so with regards to like the automation side or the scripting side, we do most of that then in Grasshopper, using Ladybug, Honeybee.
Is it, and this question is for me, is it because the software are more, the result coming from the software are more reliable and have been shown very conclusive, or is it just a personal preference?
With regards to Grasshopper, it's so like the company who really started this like successfully was Bentley, who started with through their connection through MicroStation. However, the problem was that the platform provided was very limited in terms of how much sharing there was online, the access to licensing, and so on. While with Grasshopper, the licensing is very cheap for students, and once you have a student license, you can use it commercially as well. So there's lots of people using it, and then people share a lot online. So, and that developed in the community, which supports a lot. And so mainly is the how wide it's spread due to this open source tools which are available for free. So what is available for free is the interface to the actual engines, which are the industry respected engines which most softwares use, like Radiance or Energy Plus. So it's more because there were some authors which decided to provide these tools, these interfaces for free, which made it so easy, which is mainly Mustafa and Chris Mackey, who might know them, that kind of started all this like easy access compared to other softwares.
We have another question. So when you design for international context, not in the UK, do you find limitations to collect on-site microclimate evidence and or updated climate data? What extra measure for the project you take?
Well, I think climate data is not just internationally, but over here also to get the accurate climate data is quite challenging at times because there are different weather stations. So when you're selecting a site, you have to make sure that you're selecting the right weather station, even here in the UK. So yes, that's always, we use Meteornom to get the data sometimes, or if we can get a more detailed data from the Met station from that location, we do that. But yeah, that is one of the challenging bits of doing the climate analysis.
Just like for early stages, I'm sharing a link here which has quite a large access to weather data. But as Deepika said, one has to look at the sources because this is a map of weather data. But then when you click on each of them, it tells you what the source is, and there are like different ones that have different amount of, let's say, reliability in a way. But yeah, and of course then the discussion, I see another question, I think is talking about warming climate. So then there are also weather projections or climate projections of what the weather would look like, let's say in 10 years, 20 years, and so on. So one would also look at those.
Okay, thank you for that. Another question, how do you ensure the occupants and the maintenance team understand the principles of the building? Do you ever find that they don't fully understand, which leads to problem? Example, complaints, not using correct glazing when replacing Windows panels, increasing set points of chillers.
If I may go on this one. So I think it depends also on the client as well. So let's say with LSE has been like an ideal client, so we would typically have an agreement that we continue assisting on the project and following up, and we would be doing a post-occupancy evaluation. So with that type of client, it's easier because one has that, like, in a way, like a period where these items can be covered. However, the one that would not be covered would be like replacing the window, because let's say that might happen like in 15 years time. And so yeah, it's important that the data is, let's say, stored correctly, that there's access to the data. So once one is required to check, can refer to. Yeah, typically we would be there for the to make sure that the installation has been done correctly, and then we can like prove it that things are working well, and we would provide guides to the team, and we would even be still on the project for a few months to make sure things are working well.
Yeah, just to add to that, I mean, like Harman said, LSE is a great client, so we have the soft landings appointment as well. So we are getting all the energy data back from them and assessing them. But this is where the whole discussion about energy monitoring and design for performance and everything is coming into effect now. There's a lot of noise, which everyone must have heard of, which is energy in use targets and energy monitoring and disclosure of the data, which is becoming, which is exactly answering that question, of making sure that whatever these, complex controls are being designed, they're actually being used in the project. So it's very difficult to ensure it, and it depends from client to client, and it's much more difficult to control in office buildings, for example, because when you're designing these buildings, you don't know who actually will be moving in and how they'll be using the space. But with LSE, it was slightly easier because it started only with very, very detailed conversations, but we still have a soft landings agreement with them.
Thank you for that. Another comment is pretty interesting. I'm just thinking that the amount of resource you need to produce these models, graphs, studies seems enormous. From practice, we know that large projects get very demanding regarding the timescale. How do you cope with that? Do you try to automatize most of it?
So typically we try to, let's say, like learn from previous projects. So for example, if we did a script which has an element of automation, we would use kind of part of that for the next one. So then instead of, if we spend, let's say, 3 days developing a particular script, then for the next project, we can dedicate those 3 days rather than for doing the same type of automation to enhance something further, let's say, maybe with daylighting, which before maybe focus more on thermal. So we try to, in a way, like learn from previous scripts and enhance them. However, so instead of basically, with regards to resourcing, what the difference is that it allows us to explore more options. So while in the past we were doing similar things. So when we look at the Toulouse School of Economics.
Armin, are you still with us?
I think the connection just dropped. So just to complete, I think what Harman was saying. So basically we use, he's back.
Oh, you're back.
Okay, so for example, if I take one example, I showed one image of the Toulouse School of Economics. So for that one, we did a similar type of automation, but all manually. So it took lots of time to make all the different things manually, all the different orientations being tested manually. So nowadays we're trying to have an element of automation to that, and once we invest in that, dedicate some time, we know that eventually we can use at least part of what we're investing into for a different project as well. So it requires an element of investment of time, but in a way then it allows us to explore more options. Like while otherwise we would have explored 3 glazing ratios, for example. Now it allows us to explore, let's say, more glazing ratios or more fin depth. So it allows us to be, let's say, more accurate in our recommendations in a way. But
good. My question is, are you the one initiating the conversation with the client for all these amount of work and all these analysis that you perform, or is it them who comes to you with like kind of an idea of what they want? Because we tend to say that the client are not willing to pay. So are you the one who pushed them to put the hand in the bucket?
I think I would say to a certain limit, we drive it, but also in some projects we get a brief, and with the whole new zero carbon thing, at least they know that this is what they have to achieve. So they usually come with, okay, how to go about it, how to achieve zero carbon, and then you can almost drive it because it's an open forum then, and you're gonna say, okay, you can do this, and this. So sometimes you get good clients who are well informed. And architects especially, they have a lot of knowledge themselves, so they would drive it as well. In some cases, you have to almost do the hand holding.
I think when it comes to also the cost benefit, like especially for clients who are builders and occupiers like LSC. So the actual cost for the consultancy is not very significant. Consider that many times we're under pressure lawyering to turn this around in 2 weeks or 1 week. So the amount of time that even physically we can invest so is still limited in a way. And so when compared to how much energy they will save, for example, over the next, let's say, 20 years, it will be like the benefit is there. And some architects are very keen on it. So like say architects like Grafton Architects, Rogers Tech Harbor, they would come to us to actually assist kind of like how deep should this fin be, or where should we put the fins. So that one is like part of the architecture expression rather than having it as an add-on, like we designed this, now help us to pass for. And one last point is, and policy is moving a lot, is pushing a lot as well now. So lots of these overheating studies, for example, are now required by policy, while before we were doing it as a good practice kind of thing. Now it's mandatory, for example, within London for major projects and so on. So policy is driving it a lot as well now.
If I can add one last point to this, you will see a lot of clients now coming with this, because now there are new things like carbon tax and carbon funds, and the loans that you're getting for your buildings, they will have all these metrics and benchmarks. So you will see a lot of all this conversation coming from the other end, where they'll be saying, okay, are we meeting these benchmarks? Are we meeting these targets? So for clients, it's always going to be a cost discussion. If you present a solution and you present cost benefit of that, or value to money, the chances are that they will buy in.
It also have an enhanced asset value as well at the end. So because at the end, like saying, even if there isn't a carbon tax right now, but we know that let's say in 10 years or 15 years down the line, it can be more expensive to refurbish it, etc. Or also risk to, let's say, mold growth, for example, if the surface is too cold, etc. So there is that element of enhanced value as well. For a little, we know our fees typically are quite very, very tiny compared to all the cost involved in planning. So, and the importance is that to have the advice early on. So if somebody comes, let's say, a few months before construction, then it's a problem because so much work has been done. But typically, if we're, let's say, early consultancy beginning, like stage 1, stage 2, that's where we can bring, let's say, the most value for money in a way, because with a few indications, we can, let's say, steer in the right direction. I think that's the most important stage, I think.
We have one last question. What are your recommendations for future-proofing our buildings for a warmer climate?
To this, let's say we worked on many projects. Let's say a number of projects in Paris and Toulouse and so. So I would expect similar approaches which we had in warmer climates will be applicable. But in our simulations, we already account for that by using projected weather files to see how it will perform. So yeah, one would definitely look at the use of solar control, like an overhang, for example, or the type of glass used with a low G value, and also one of the items probably which maybe has been how to say, like has been ignored maybe in the past was the openable window area, especially if you have some types of accommodations, for example, like student housing. Many times for safety, you have very small openable area, which then you have small spaces, they tend to overheat. So openable window area is also very important. Use of thermal mass and solar control. I think those three are the main.
I think I'll add to that, I'll say adaptability. So you have to design your building thinking about current weather and future weather. So when we're talking about, mixed mode ventilation and everything, it might not be as beneficial in, currently in time. Maybe it gives you a 50% improvement, but in years, years down from here, from where we are, it might be giving you a 70% benefit. So when we are designing, we're always doing the analysis of current and future weather data and providing solutions for that. And as Harman said, thermal phase change materials, all these different solutions, they are answer to those future climate scenarios.
Thank you both so much for such an insightful presentation, especially for the work that you've shared with us today. And thank you for being with us today. Thanks a lot. That will be all. Thank you all for attending, and hopefully, and keep following us on social media so that we can always be informed on our next CPDs. Thank you all. Cheers. Bye.